Okay, everyone, and welcome back to our scientific and meteorological use of spectrum presentation. We're very pleased to have Dr. Jordan Gerth here, and just want to give you guys a little introduction to him for those of you who don't know him. So, Dr. Gerth is a physical scientist, the leveraged operations lead, and subject matter expert for weather satellites at the National Weather Service's Office of Observations. His primary area of interest is the development and transition of meteorological observations and research, particularly involving remote sensing into the operational weather forecasting environment. Dr. Gerth is currently developing National Weather Service requirements and a mission concept for the next generation of geostationary weather satellites under the GeoXO program. He also leads a team of government contractors conducting meteorological research, usage engagement, and software development for operational users. Dr. Gerth previously developed atmospheric science software applications and stakeholder communications related to weather satellites. So quite a deep well of information we have here in front of us. Welcome aboard, Jordan. We look forward to hearing your thoughts, and feel free to take it away.
All right. Well, thank you so much, Joe. Really appreciate that introduction and really appreciate the opportunity to speak to all of you this afternoon. I just want to confirm that you're seeing my correct slide and not my notes slide. Is everything looking good?
Everything's looking great. We've got a wonderful looking cover slide.
All right. Perfect. Yeah, so the title of my presentation is, can you turn that down, please? And I'm going to be talking about the prospect of 5G signal interference with meteorological observations. I'll tell you, before I get started here, a little bit about my journey into the area of spectrum management. I was an atmospheric science student, just very much interested in the atmosphere, and all my friends were chasing tornadoes across the plains. And as I was going through my graduate work, this topic really started to come to the forefront, and talked to a few people that said, we really need some more attention on this. We can't take spectrum holdings that are used for atmospheric sensing for granted anymore. And of course, all of you are very familiar with the NTIA and FCC processes. And I'm going to talk a little bit about how we got to this point and some of the outlook. Looking forward to your questions at the end. Also, just note that I am the chair of the AMS Committee on Radio Frequency Allocations, and some of the information in this presentation came from my fellow committee members. As an atmospheric scientist by background, I'm very thankful to have folks that work in the policy, legal, and engineering sides to kind of help fill out, complete my breadth of information on this, and I'm always learning. So let's go to hopefully something that everybody appreciates. I know that it's an easy joke. Every time you talk to meteorologists, I hear it probably too many times. The most unoriginal joke, yeah, you get paid for being wrong half the time. And I just hope that if you take away one thing from this presentation, that weather forecasts have never been more accurate. And it certainly was true if you dial the clock back, even 30 or 40 years, that the accuracy of weather forecasts was a lot different than it is today. And you see there, a 5-day forecast today is as accurate as a 1-day forecast in 1980. So I like to tell people, if you just laid out, selected your clothes attire for the whole week on Sunday night, that's as good as picking out your clothes the night before in 1980. So we've had a lot of progress, and weather satellites and remote sensing is partially responsible for that. Also, it's easy to say that everybody uses weather forecasts, but you may not know the quantity. The US adults obtain about 300 billion weather forecasts per year. So on average, the average adult is checking the weather 3 times a day. So if we were in the room together, I'd probably ask you to put your hands up and say, who's looked at the weather in the past 24 hours? And most people are weather aware for one way or another. You're deciding what to wear. If you're in a business that's weather sensitive, like pouring concrete, construction, You got evening events. You're wondering, can we, eat outside tonight? Whatever it is, people are very attuned to that, and I think that's great. And I'll also note that spectrum and people that are using cell phones to check the weather is one of the main ways that they're accessing those weather forecasts. And so when we talk across our weather enterprise, we make sure that we explain that, yes, there's a lot of weather observations that are collected with spectrum allocations, but it's also the communications is fundamental. I won't talk about the EAS alerts here other than to mention that, if there's a tornado warning, there's a way to activate that on your phone now. So certainly using 5G communications is a way to deliver critical weather information. You see there on the right side that studies have shown that the value of weather forecast to US households is about 31.5 billion. So compared to the public expenditures and the private expenditures, weather forecasts deliver a lot of value to the American public. A lot of that public expenditure, by the way, goes to satellite programs. Satellite tend to be the most expensive observations that we launch, that we have, but also the most impactful. The other thing that I want to point out that you may be unaware of is that billion-dollar weather and climate disasters have been rapidly increasing. And this is just a look at the $20 billion disasters we had in the US last year. And you may be familiar with some of the hurricanes that made landfall on the Gulf Coast. There's a lot of wildfires out west. There's almost a continual fire weather season now. There's a lot of heartbreak we hear coming out of the west with the dry weather, really literally adding fuel to the fire. And then when it does rain, the rain comes very hard and heavy, parts of California. And then across the central US, there are many different severe weather outbreaks, whether that's in the form of tornadoes. Mayfield, Kentucky had a major tornado. There was also a major cold weather outbreak, if you recall, back in February 2021, stressed the power grid. So we are seeing more and more billion-dollar weather disasters. And this is how I try to quantify some of the reason that we have to continue our important investments into observations, just because there are so many weather-related impacts. And inflation adjusted, you can see here the number of events continues to increase. You'll see 2005, Hurricane Katrina. 2017, there were several hurricanes, including Hurricane Maria that hit Puerto Rico, and Hurricane Harvey. It's a major disaster for the Houston area. But unfortunately, you can see the trend here over the past 20 years in particular. We are, in fact, seeing more disasters. So it's not just that the news continues to dwell on these stories, it's that the amount of significant weather is really increasing. So the basis for improvements to weather predictions, weather observations, especially from satellites, the amount of computing power, and the development of computer models and data assimilation routines. So we have very sophisticated supercomputers that crunch the numbers, if you will, and provide us with forecast guidance out to 16 days. Those are run 4 times a day. And satellites are responsible for a large number of those observations, 95 to nearly 100%, depending on the metric that you use. There are a lot of observations from satellites. And so we're actively there's still work in progress, research and development in progress to use data to the maximum extent. The US constellation of satellites, and this is where I'm going to transition to talk about some of the more spectrum side of this. You can see that NOAA, National Oceanic and Atmospheric Administration, they launch what we call the operational satellites that serve our weather forecast. So if it's contributing to weather forecasts and warnings, protection of life and property, those are NOAA satellites. We have them in both geostationary orbit and we have them in polar orbit. The DoD also operates satellites, Department of Defense. And we also have satellites in the low Earth orbit, what we call the National Polar Orbiting Partnership, with NASA and the NOAA 20 series. And I'm going to talk specifically about those observations and their importance. One of the analogies that I like to use is that the GOES satellites are what you're likely to see on the evening news, where the satellite is orbiting with the Earth. So you're always looking at the same spot. So the clouds move, your frame of reference doesn't. But it's just some pictures of the clouds. Whereas those low Earth orbiting satellites, that's more of the equivalent of, like if it's an X-ray in the geo orbit, it's more like a CAT scan in LEO orbit. So we're seeing underneath the clouds. There's more to see, and that's where these spectrum issues are largely arising. So what parts of the spectrum are we using? Well, we sense a lot of the atmosphere in the visible and infrared. So that GOES satellite is sensing visible and infrared only. Obviously, infrared's important. Well, maybe not obviously, but infrared is important because we don't have visible light at all times of the day. And so our meteorologists need some way to keep track of the clouds and storms at night. The microwave between about 1 and 100 gigahertz here is what we use with some of the polar orbiting satellites. So that just gives you, we are on this interface between the radio spectrum and the optical spectrum, and that's why some of these conflicts are coming up. And the first time that this really spilled out was back in the spring of 2019, about 3 years ago. The topic matter was some spectrum around 23.8, 24 gigahertz. When NOAA and NASA were essentially calling on the FCC to halt their auction, to get their ducks in a row because there was concerns about the quality of weather forecasts. So this is when people started really paying attention to this. This is when some of my friends that were chasing tornadoes said, you know what, you're really doing important work with the spectrum, because we were taking that for granted, and now we realize that there's actually legitimate concerns about this. And I said, of course, I'm not wasting my time on this. And so I want to break it into 3 different points that I want to make about this, because they often get confused when we talk to the media. The first one is that there are observations at risk. So we're concerned that high-powered terrestrial wireless emissions in or near spectrum allocated for Earth sensing will reduce consistent and reliable global weather observations. And that's the microwave piece of this. There's also been the Weather Enterprise, the AMS, has been concerned with issues related to transmission and moving data down. That's collecting the data from the satellite to users, whether those are industry, America's private enterprises, or to government users, which are at least partially protected. And then the other point is sometimes you'll hear these larger claims about, well, if we have RFI with satellites, weather satellite signals, that weather forecast accuracy is going to get knocked back to the 1980s or something like that. And from my professional experience on this, the risk of spectrum sharing is not necessarily a sudden decrease in forecast skill or a complete loss of observations, simply because when these 5G communications are rolled out, they're rolled out in local areas, they're rolled out in regional areas. It's not as if the whole country is all of a sudden interfered with. Now, there's a whole bunch of different problems that I'm going to explain about the rollout and being able to detect RFI and not RFI. But the reality is that it's not as if when we turn on a 5G network that causes interference in one city, that all of a sudden there's a cascading failure of all of our numerical models. So I talked a little bit about this similar but different issue. So I'm going to first start talking about 1675 and 1680, the L-band, which is transmission that we use or adjacent to spectrum that we use for satellite ground transmission with those geostationary satellites that I showed earlier. We have the primary uses are relay of remote weather stations, situational awareness of weather, just tracking the clouds, as I mentioned, tracking cloud track winds. I'll give an example of that. And of course, the imagery on the evening news. The impact to users is that they are not getting the data, and weather data is time sensitive. This is one of the challenges that we have, is moving a lot of data very quickly. And so previously, and up to still currently, although we're exploring new solutions, satellite downlinks were key because of the data rate and the type of imagery that we were receiving. I'll talk later about the microwave, which is actually listening to the atmosphere and seeing through the clouds and contributing to those numerical models, and some of the considerations for that later in the presentation. So, first topic, GOES series satellites. So here are the spectrum that we use for GOES. The spectrum proposals are on the lower end, as I mentioned, 1675 to 1680. That GOES rebroadcast, or GRB, is a 31 megabit per second link. We have 16 spectral channels coming down of data. The highest resolution is 0.5 kilometer, and we scan the whole Earth, top to bottom. Well, the portion of the Earth that's visible to the satellite, just to say what we call the disk, every 10 minutes, plus images of the contiguous United States every 5 minutes, and even some imagery as frequently as every 30-second small postage stamps. We also have the DCP report relay, the data collection platform report relay, 1675.7 to 1680.4. So that's really right on the edge, and that's where a lot of concern is. What that is largely remote weather stations. And you can see where we are in the mission timeline here. This is a 4 satellite series. We just launched the 3rd one in the series on March 1st. There's 2 of them active at any given time, one along the East Coast, one along the West Coast, that also services Alaska and Hawaii. And upstream weather, that's what builds our forecast accuracy out to that 5, 7, 10-day range. And you can see mission timeline takes us all the way to 2040. So we are planning and considering how to best make use of our spectrum resources for the 2030s and whatever follows the GOES-R program, the GOES-R series, because we need to continue this capability. But these satellites and this spectrum is going to be continued to be used until the last satellite, GOES-U, which will launch in a couple of years, is near end of life. Which is usually about 8 to 10 years after launch. So this breaks it down, again, in a format, more visual format for you. The data collection, the proposed share for 1675, 1680, what it's up against is the relay of flood and tsunami warnings, river and coastal gauges, fire weather sensors, inland river navigation and drought management. That's what GOES data collection is used for. And that's in addition to the GOES rebroadcast, which is the imagery. There you see a picture of a hurricane that comes out over the rebroadcast. So it's that and the imagery that our forecasters use to track the storms. And then there was previously an AWS-3 auction, which is actually why we compressed some of this. And there's some emergency management and reduced data feeds. Those warnings are disseminated over those channels. And our legacy polar satellites are also up there as well. Although our oldest polar satellite just turned 24 and is still in operation. It's 24 years old. It was launched in May 1998. So some of these satellites, really, we do get a lot of value out of them. People ask me, what's the importance of GOES data? This is the eruption of Hunga Tonga in the South Pacific earlier this year. This is this particular eruption sent shockwaves around the world. We're actually able to use satellite imagery to track waves in the upper atmosphere that were caused as a result of this extremely explosive eruption. One of the most explosive eruptions, I think the explosive eruption since 1991. So this is the kind of imagery. Unfortunately, we didn't get the higher resolution imagery, but we get 10-minute, and you see how it goes from a beautiful day in Tonga to an absolute significant eruption and cut off communications, and really striking how quickly volcanoes can change the atmosphere. Let's see here. Trying to push it onto the next slide, but that's a pretty big animation. So let's see if it'll go. There we go. All right. The other thing that's important to keep in mind of why we're concerned about spectrum radio frequency interference for weather is that we need to have consecutive images. So most of us fly on airplanes, either for business or leisure, and aviation is hugely weather sensitive and hugely reliant on weather and satellite observations. What we can do with consecutive satellite observations that are clear is calculate the winds. So as the clouds move, you can see there in the red that those are what we call wind barbs, and essentially the flags. If you see the little triangle, that's 50 knots. This is the lines are 10 knots and the smaller lines are 5 knots. And you just essentially add them up for an indication of the wind. And then I have all the airplane reports for turbulence and such layered on top of them. But this is critical for them because airlines do not want to fill their flights up with more fuel than they need. They don't want to burn more fuel than they need. And understanding the wind regime is a critical aspect of that. So there's a clear reason why we want to eliminate as much interference with the transmission of the data as possible. It's not just that, well, we get 1 or 2 bad images like you could on a TV signal. It's that really we would interrupt the calculation of important atmospheric variables that play into weather sensitive industries. Okay. All right, so this is these are the locations of the remote weather stations, or what we call the RAWS stations, and these support incident meteorologists and wildland firefighters, particularly in the Western United States. This data is relayed through the GOES series. So because they're remote, we really need to get this information down as weather events, wildfires rapidly evolve. The ability to have remote weather stations and get that data to support our firefighters is another key use of GOES. So this isn't as much using the imagery. This is using an uplink and then a downlink to the necessary agencies that are involved in positioning this equipment. This is an example from the previous version of GOES. It's a little more analog than what we have today, which is a digital signal. But this is essentially what interference looks like. And this is why we're concerned about it. You can see there's certainly stripes through the imagery. We don't want to have that happen when we're trying to monitor a storm. You can see the tropical belt is cleared out. Now, of course, as subsequent images come in, you get other parts of it and not others, but it really makes it challenging. And I think this visualizes the real concern that we have. It's not like we can necessarily use terrestrial delivery, although we're exploring solutions to protect only one part and then federate it out. But right now, if there's a user that receives interference, that they're also not receiving their imagery. And this is what it looks like today with our digital signal on the new generation GOES. You're essentially just losing a block of the image. So as thunderstorms are developing, thunderstorms, average lead time for a tornado warning is 10 minutes or so. Strive to have it 15 minutes. We don't want to be losing intermittent pieces of that data that contribute to those warning decisions. The other thing about the LBand, so that was all related to transmission. This is actually related to collection. It's something called radio occultation, which is an anchor observation that uses GPS satellites and another satellite and the path, the bending angle through the atmosphere to determine exactly what the state of the atmosphere is between the GPS satellite and, in this case, the cosmic mission. We're able to use radio occultation profiles, particularly over the mid-latitudes and the tropics, to bias correct other satellite observations that we receive that I'll talk about in a minute. The challenge is with GNSS receivers, any RFI with GNSS is also a threat to our use of that our cosmic mission or any of our radio occultation data. And we're starting to see that about 5 to 10% of our radio occultation measurements are actually interfered with, most probably through illegal jamming. And a lot of that, I don't know a lot of it, but at least some of it is occurring in Europe with truckers that I guess are trying to prevent them from being monitored while they're doing their route. So, and this is an interesting and evolving area that we're trying to learn more about and the consequences of. We certainly don't. We're able to tolerate 5 to 10% loss because we do receive a lot of these radio occultation profiles. But if it got even higher, it would be consequential. And I question whether I should go a little bit into the weeds here, but I will, just to explain exactly how forecasts are sensitive to observations in this chart. And this is a really good example because we were, as meteorologists, we were panicking a little bit at the start of the pandemic. Of course, we were concerned about the pandemic, but what we were concerned particularly about is this teal line here, is the loss of aircraft observations, which were at the beginning of 2020, one of our most fundamental observations for maintaining the accuracy of weather forecasts. And as everybody knows, there was substantial reductions in the amount of aircraft flying at the beginning of the pandemic. And to some extent, globally, it hasn't fully recovered yet. So what happened was, this shows forecast sensitivity to observation impact, essentially how much impact each observation is having in the quality of a weather forecast. And we were fortunate to have our radio occultation mission come online right as we were losing a lot of aircraft data to support our weather forecast. So that jumped up, and then a commercial company, knowing that we were in a bind, gave us a temporary period in the summer of 2021 to use their data as well. So that radio occultation data, again, this is the data that 5 to 10% of it is interfered with, was a huge contributor with the loss of the aircraft observations, or at least a partial loss of the aircraft observations over portions of the globe. And this is, by the way, for the European model. You may hear about this. Europe has a global weather forecast model. Next, I'm going to talk about this black line, which is the microwave water vapor, which has come under threat of that 23.4 gigahertz, and other channels contribute to that. But I just wanted to make the case here that really, since the pandemic started, radio occultation is on par with the aircraft data to have a resilient set of observations driving into our weather forecasts. So next, we're going to talk about the collection side. And this is, again, this is more of the CAT scan. So some of you may be aware of this, but just to clarify, molecules in the atmosphere emit radiation that we're trying to sense with satellites. So most people know that atmosphere largely consists of nitrogen, oxygen, and argon. We don't sense those as much as we try to sense carbon dioxide, and we do sense oxygen, but also water vapor. Water vapor is a hugely variable quantity in the atmosphere. I know we usually think like the atmosphere is largely oxygen, nitrogen, but water vapor on very humid days can constitute up to 5% of the molecules that are out there. So that water vapor, as I like to say, is the most significant greenhouse gas, and is very important for understanding the temperature of the atmosphere. So the radiation that the satellites are sensing is essentially the background. It depends on the temperature and the quantity of the molecules, the atmosphere, and the land or water surface underneath it. If the atmosphere isn't thick enough, that frequency is our signal. So sometimes when we talk with people familiar with telecommunications, they're talking about filters, signal. There's no, the radiometers are just sensing the raw radiation, so there's nothing to separate. And we're looking at ways we can identify that, but that's where this is the foundation of this problem. And there's a lot of different frequencies that we use for our different satellites. You can see we have the Defense Meteorological Satellite Program, DMSP, uses 23.8. POSE, the previous NOAA series, uses 23.8. The new JPSS, Joint Polar Satellite System, and National Polar Orbiting Partnership also uses 23.8. We're concerned about the channels in the 50s. These are sensing for temperature in the atmosphere, which is a very important quantity for us. And then some of these higher bands are used for precipitation, cloud and precipitation sensing. This really just summarizes what I just said. I show this just to give you an example of footprint size. Essentially, the pixel that the satellites, excuse me, are sensing, and they're somewhere between 35 and on the lower end, they're between 35 and 75 kilometers. So you get closer to 183. We have about a 16 by 16 footprint, and it does depend. There's some parallax scanning as we sense away from looking straight down. There's some broadening of the pixel size. So just to visualize what the data looks like, this is the NOAA 20 satellite, and you can see here it goes, it gives us a nice orbit, fills it in twice a day, and the water vapor concentrations are highly variable across the Earth. I am mindful of the time here if somebody's tracking that, so I'll try to wrap this up soon. All right, so this is what interference looks like. We've seen this before. This is data from a Japanese satellite, near 7 gigahertz. We see this routinely. This has just happened to be on October 2020. But you can see cities, New York City, Washington, D.C., Baltimore area, Atlanta, others out west. The challenge is, some places it's obvious. Other places it's not so obvious. For example, in the Midwest, what is meteorological, what is coming from interference from terrestrial signals. And we're continuing to use and improve weather forecasts based on this data. In 2006, only 6% of weather forecast skill was based on microwave water vapor observations, whereas now we're up to about 20%. And over oceans, that can be as high as 25 to 45% of the skill is going in is coming from microwave water vapor observations. This is an example of what water vapor, this is what example of what microwave weather observations look like for Hurricane Dorian. Again, you can see beyond the cloud structure. It doesn't have that iconic look to it, but you can still see the eye wall, and the feeder bands, all important information. And these are the different satellites that sense in that frequency. All right, so just to wrap up here, there's 2 issues, one of which is transmission. The other one is collection. We have a lot to be concerned about when it comes to collection, particularly because there's more and more 5G services moving to greater and greater frequencies. Lastly, I just wanted to give a brief note about Nexrad. You may know that we have about 159 Nexrad radars across the country. There's very few other operators in the S-band. Weather radars are used for severe weather warnings, monitoring precipitation. So this is what we use for that tornado warning that comes across. We have about 10 to 14 ongoing issues, interference with radars at any given time. Most common sources of interference actually are other radars, FAA and DoD, atmospheric surveillance or aircraft surveillance radar systems in the 2700 to 2900 megahertz band. Although cell towers are also becoming an issue. And out-of-band emissions can affect the Nexrads up to 2765 megahertz. Other things occasionally happen. There's some artifacts and radar imagery. It tends not to be the largest concern most of the time. However, this is what it looks like. There's these large spikes. You can tell it's not really meteorological. It doesn't look like rain or anything, but if there's enough of this, that's something that can interfere with a meteorologist's ability to track rotation and storms and major events. So we work to actively eliminate that. So in summary, weather forecasts improve annually, largely due to satellite observations. Delivery of satellite weather data must be timely, consistent, and reliable. That's what we're after. The atmosphere emits microwaves that are useful to sense. Hard to sometimes talk to the public about that because there are some conspiracy theorists. I can go on and talk about calls that I've received about people that tell me that the microwaves are interfering with their ability to think during the day, and that I need to talk to their doctor. And that's been an interesting insight into that segment of society. Many weather satellite missions last 10 to 20 years. Spectrum sharing proposals are proceeding much faster. Some of these issues with the delivery can be solved if we wait until the next generation of satellites. But the spectrum sharing proposals want to move much faster. I understand the motivation for that, but it is challenging. These satellites are multi-billion dollars a piece. Most satellites that we launch are usually a minimum cost of about $2 billion. So they are expensive. And then finally, the impact of RFI on weather forecasts is not going to be immediate, but it could become more consequential if it expands, which is why we're trying to get the word out about this. We certainly do want to work with industry to try to find a way to move forward so that there's not interference and that they understand exactly what we're trying to accomplish with our measurements. Also, as I hope I proved to you, the value of microwave observations or microwave water vapor observations isn't achievable through other means. It's not a matter of, well, if we launched a few more weather balloons, we can solve this problem. Microwave observations over the oceans, over data sparse areas, even over the United States are very important for the accuracy of storms, especially if we want to push the frontier of weather forecasts out to 10 days into the future. And there's a lot of good reason to do that, particularly with the storms becoming much more frequent, to give people more precision, more lead time, more ability to prepare and evacuate and protect their property and their lives from dangerous weather. Weather satellites cannot filter RFI. RFI and atmospheric radiation are inseparable to a radiometer. So if there's some that's not being some 5G signal that's being refracted up to the satellite sensor, we don't know how much of it is natural versus unnatural. And that's a huge problem. It's one thing to filter data out from our models that we know is corrupted. It's a whole other thing when the data that we're collecting, the bias is uncertain. And then, as I mentioned, the weather enterprise is in search of engineering solutions to apply to ground networks to adapt to the new spectrum landscape. We understand that spectrum is a finite resource and we have to manage it effectively, and that we shouldn't necessarily take it for granted, and the spectrum that we use, the use of it must be well explained, and so that we're able to communicate the value very clearly and understand why we need to preserve it and protect it against other uses. So with that, I really appreciate the opportunity. As I said, as I started my meteorology career, I'm not sure if I ever thought I'd be talking to the National Spectrum Management Association, but I'm glad that you have open ears for this. And if you ever have any questions, please feel free to get in touch with me, or whatever time we have remaining, I can take them now.
Great. Thank you, Jordan. Very, very illuminating. We do have a couple questions. I think we can try to squeeze them in. First is from Bo Backus. He says, excellent presentation. Thank you. Our dependency on the microwave passive bands is very apparent. What sort of approaches are being considered for protecting our passive band measurements? And should we reduce our future passive band sensors for addressing this issue?
Should we reduce the amount of passive band sensors in the future?
I assume that was a tongue-in-cheek.
Okay.
But the first part, what sort of approaches are being considered? Yeah.
Yeah, I mean, so what we're trying to look at is, first of all, can we lower?
Oh, I'm sorry. He said, should we redesign, not reduce? Should we redesign?
Okay.
Yeah.
Okay. Well, I think that we have to, first of all, I don't think there's an alternative for microwave remote sensing. So hopefully, first and foremost, that's key. Now, keep in mind when these satellites move, as I showed in that video, that they're only sensing the atmosphere at the time that they're overhead, and they're not lingering very quickly. These orbits, I should have mentioned, are only about 100 minutes pole to pole. So, there's some research going on currently to figure out, well, can we shift temporarily as a satellite's passing overhead or lower the signal from these terrestrial networks to reduce or ideally eliminate the likelihood. The other possibility is if we can understand the RF environment before sensing occurs, to understand exactly how much interference is encountered in the atmospheric signal. That's another key part of this. Understanding the RF landscape to make sure we're not using data that's not of the highest quality would be key. Of course, that's eliminating data that we could otherwise be using, but it does solve perhaps half the problem of incorrect forecast resulting from incorrect data.
Interesting. Thanks for that. Renee Leduc says, hi, Jordan. Thanks for the presentation. Any thoughts on how the atmospheric science community can better communicate its complexities to regulators and the wireless community? Also, there was just a side note from Michael Jamelko, who just said, hi, Jordan, great presentation. So.
Well, okay. I didn't realize I had a few friends on the call just saying hello, but hello. Yeah. We have to do better. The Weather Enterprise has to do better. I think we are actively working to communicate the value of spectrum holdings and the science case. I think one of the things that's missing in the process right now is that the science really isn't taken into consideration. Like we don't hear people considering the value of the weather forecast, the value of the spectrum holding for the purpose of meteorology and everything that goes along with that. So I'm all for getting everything on par in terms of better explaining the independent value of spectrum holdings for improving meteorological services compared to just what the value of the spectrum is going to be for 5G or other purposes.
Yeah, you had some pretty compelling slides there about the the $1 billion storms. For example, the array of satellite networks that are out there, how they're serving, and how gaps, and of course the pain of interference and what that means. Because it's not just $1 billion. Sometimes we were talking like you mentioned, life and limb, and that's not for nothing. We don't want to be dark in those critical moments. Well, thank you. What a pleasure to have you on board. Hope we can have continued dialogue, and NSMA is here for all aspects of spectrum management, and of course the weather satellite community and weather prognostication writ large is part and parcel of that. So you always have a home here. So.
All right, I appreciate that. Right. Always trust the weather forecast. That's what I'll tell you. Take care.
All right, great. Good to see you. Take care. Well, coming up, we're going to have our working group 3 helmed by our board member, David Meyer, former president of NSMA. I'll see you folks there on that panel. Thank you.